Let's analyze the rectilinear motion of a point. Figure 1.1 shows the distance traversed by the point as a function of time. Using this graph, we need to find, first, the average velocity of the point during the time of motion. Second, the maximum velocity. And third, the time moment t0 at which the instantaneous velocity equals the mean velocity averaged over the first t0 seconds. Let's start by reconstructing the graph shown in the figure. We have time t in seconds on the horizontal axis, ranging from 0 to 25 seconds. And on the vertical axis, we have distance s in meters, ranging from 0 to 2 meters. The curve shows how the distance changes with time. It has an S shape, starting slowly, then accelerating in the middle portion, and finally leveling off at about 2 meters. Let's solve part A, the average velocity of the point during the entire motion. The average velocity is defined as the change in position divided by the change in time. From the graph, we can see that at time t equals 0 seconds, the distance s is 0 meters. And at the final time t equals 25 seconds, the distance s is 2 meters. Therefore, the average velocity equals 2 meters minus 0 meters, divided by 25 seconds minus 0 seconds, which gives us 0.08 meters per second. Now let's tackle part B, finding the maximum velocity. The instantaneous velocity at any point is the derivative of the distance function, or graphically, it's the slope of the tangent line to the st curve. The maximum velocity occurs where the slope of the curve is steepest. Looking at the graph, this happens around the middle portion of the curve near the inflection point. Let's draw a tangent line at this point, around t equals 12 seconds. To estimate the slope, we can measure the rise over run, from t equals 10 seconds where s is about 0.6 meters to t equals 14 seconds where s is about 1.4 meters. This gives us a slope of 0.8 meters over 4 seconds, which equals 0.2 meters per second. This is our maximum velocity. Finally, let's solve part C, finding the time t0, at which the instantaneous velocity equals the mean velocity averaged over the first t0 seconds. Mathematically, we're looking for the time t0, where the instantaneous velocity, which is the tangent slope, equals the average velocity from 0 to t0, which is s of t0 divided by t0. Graphically, this is the point where the tangent to the curve at t0 has the same slope as the line from the origin to the point at t0. Let's visualize this by moving our tangent line along the curve until its slope matches the chord from the origin. This occurs at approximately t0 equals 12 seconds. At this point, the instantaneous velocity equals the average velocity over the interval from 0 to 12 seconds. To summarize our results, the average velocity over the entire motion is 0.08 meters per second. The maximum velocity is 0.2 meters per second, which occurs at the inflection point of the curve. And the time t0, at which the instantaneous velocity equals the mean velocity, is approximately 12 seconds. Physically, this means our object started slowly, accelerated to reach its maximum speed at around 12 seconds, and then gradually decelerated until it practically stopped at around 25 seconds, traveling a total distance of 2 meters.